This meeting is being recorded.
Okay, so hi everyone, thanks for coming. And so today I'm going to be talking a little bit about my research on developing a deep learning approach to map infrastructure across the Arctic from sub-meter resolution Maxar imagery. So let's see. Sorry, I'm trying to figure out what is right. So we know that permafrost built upon infrastructure built upon permafrost relies on the mechanical strength of the underlying frozen soils, which in turn depends on stability of ground temperatures, right? And this creates a number of widespread hazards for Arctic infrastructure, namely in the form of decreased ground bearing capacity, ground subsidence, and deformation of level surfaces, right? And so in response to this, a number of risk assessment studies in recent years, like the one portrayed in this map, have mapped permafrost geohazard potential, mainly using data on ground ice content and future active layer thickness and ground temperatures. And so they've mapped this geohazard potential in relation to infrastructure using the most current available data to identify at-risk areas and quantify the socioeconomic costs, right? However, the most common challenge across all of these risk assessment studies is access to geographically complete and up-to-date inventory on Arctic infrastructure. So a lot of these authors acknowledge that their studies might be significantly underestimating the costs because of this. So satellite-based remote sensing and mapping actually is really well suited for addressing this data gap. However, as of now, there's only been one attempt to do this. And this was done by Annette Barsh and her co-authors, who developed the first automated machine learning deep learning workflow for Arctic infrastructure detection using Sentinel-1 and Sentinel-2 imagery, right? So this was done at the 10-meter spatial resolution. And this results in the first pan-Arctic satellite-based record of infrastructure, and they call this data set the Sentinel-1-2 derived Arctic coastal human impact data set. So in particular, their algorithm has mapped classes like linear transport infrastructure, so roads and railways, buildings, and other impacted area. So looking at this figure I pulled from a recent paper on this approach, you can see that their algorithm really produces really well, really high quality segmentation results at the 10-meter spatial resolution. So this naturally begs the question then, what can we do at an even higher spatial resolution? So here at our lab at UConn, we have access to Maxar satellite imagery across the entire Arctic. So we have the opportunity to answer this question: can we enrich this satellite-based record of the human footprint using a deep learning approach with Maxar imagery? So for example, can we detect subclasses of buildings? Can we detect really small features like pipelines, for example? More importantly, can we map structures as individual separable objects in order to get the most accurate estimation possible of the area of at-risk infrastructure? Now, obviously, classifying infrastructure at the sub-meter resolution is probably a little more difficult than doing so at the 10-meter resolution. So the first question we have to ask ourselves is, in developing this approach, is how do we define the semantics of infrastructure objects while simultaneously considering computer vision capabilities and real-world relevance? So when it comes to a lot of common non-building structures like tanks, pipelines, roads, runways, gravel pads, defining their semantics is pretty straightforward, right? Because the labels we assign these structures as humans typically correspond to one very intuitive appearance. So there's no need to dwell on semantics in this case, right? But when it comes to buildings, defining their semantics is not so trivial. It can be approached in a number of ways. So in geography, urban planning, GIS, for example, building types are most commonly classified based on their functional use. Like, is this residential, commercial, public, industrial? But these are super high level semantic interpretations that can be rationalized by humans, but not so easily by a computer, right? Because they don't always correspond to object types that can be drawn from the satellite image. So for example, all three of these buildings can be considered residential buildings in their respective geographic regions across the Arctic. but they look completely different, right? So should we tell a computer then that these are the same kind of building? Here's another example. Are these stores, factories, or schools? There's really no visual cues existing in a satellite image to answer this question reliably, right? So it's much more practical to classify buildings based on their exterior appearance visible in a satellite image. And so I'll just quickly go through these. This is how I've subcategorized buildings in this deep learning approach. So you have the detached house, which is this small rectangular object that typically the smallest type of building, and they kind of have, you can see that they have pitched roofs, and they mostly occur in neighborhoods, right? Then you have the row house or terraced house, townhouse, you might hear people call it. This is a spatially continuous collection of several dwellings and that are attached together. And the key giveaway here is a repeating roof pattern, like chimneys, for example. So these black circles in this building, these white circles here, right? And then you have the multi-story block or apartment blocks, right? These are basically elongated rectangular objects. And then you have the non-residential buildings, which don't necessarily, are not necessarily confined to one regular geometrical form. So they can really look, they have wide-ranging geometries. So this is the infrastructure typology that I've synthesized. And so basically it breaks down into building and non-building infrastructure types. And so some of the key points here are that this accounts for most of the features of the Arctic built environments. And each object type exists in sufficient amounts to be sampled for model training, right? Because if you attempt too fine-grained of a classification, you'll end up with classes that are super specific and very hard to find, right? And more importantly, each structure can be linked to construction and replacement costs in the context of risk assessment, right? In particular, the fact that I've subcategorized building types is important because we know that different structures cost different amounts of money to be built. So this could help risk assessment studies have even more accurate estimation of costs. So now that we have the classes that we want to train the deep learning model with, how do we then efficiently build a deep learning training data set while also accounting for regional variability? So basically, the Arctic built environment as a whole can be broken down into 4 different settings. You have the rural setting, which basically has the smallest populations, small number of buildings. Their buildings are small on average. You have medium density, urban, and the industrial setting, right? So to ensure that the model will work in each of these different settings, I've selected a number of rural, medium density, urban, and industrial sites across the Arctic as the model training and testing sites. So I'll just quickly go through these here. To cover the rural setting, I've pulled imagery from Nuiqsut, Wainwright, Point Hope, Alaska, and as well as Coral Harbor in Canada, and a village in Russia named Saskilak. Hopefully I'm pronouncing that right. Then to cover the medium density setting, I have Utqiagvik, then the urban setting, Yellowknife, Canada, and Norilsk, Russia, and Prudhoe Bay to cover the industrial setting. So overall, I've gathered 5,304 training samples, and I've tried to keep this number equal across I've tried to gather an equal amount of samples across the different settings as much as I could, right? So you can see that breakdown here. So gathering all of these samples requires a very time-consuming and laborious image annotation process, right? So to speed this up, I've actually made use of a number of high-quality, publicly available geospatial data sources, and I have these listed here. So City of Yellowknife, Government of Nunavut, UAF, Alaska Geobotany Center, North Slope Borough, and OpenStreetMap, right? So this really speeds up the process because you don't have to go in and manually digitize buildings or roads or whatever yourself. It's already there for you, but there's still a processing bottleneck because somebody still has to go and do manual on-screen inspection and editing of the data in order to ensure that it's paired up with the actual images that you're using, right? And so in total, I'm using 10 Maxar scenes from the Worldview 2, 3, QuickBird 2 sensors. Here's the resolutions. In total, I have 2,800 input tiles. And so now I'll cover some of the deep learning workflow and the results here. And if you do a lot of deep learning work, this looks like a pretty typical workflow to you. So the model I've used here is convolutional neural network architecture called the UNet++, which is a semantic segmentation architecture. I'm using a pre-trained backbone. The input is 3 channel tiles. So I'm using the blue, green, and red bands of the Maxar images. I'm using image augmentation, and the model was trained for 100 epochs on 3 NVIDIA A100 GPUs from the Texas Advanced Computing Center Lone Star 6 system. And in particular, I'm using class-weighted cross-entropy loss in order to address a class imbalance issue that I'll talk about a little further. And I also built the models in Python using the PyTorch and segmentation models libraries. So here's some of the model performance metrics. As you can see, the average, so basically precision, recall, and F1 score are standard semantic segmentation metrics. And overall, the model has done a pretty good job in detecting each of the 9 infrastructure classes. But if you look at the precision and recall of the building classes, you can see that the precision scores are low while the recall scores are high. This basically means that the model is able to differentiate between these different kinds of buildings, these subclasses, which is good, but it's actually overestimating the boundaries of these buildings for some reason. And I'll talk about that a little further. But overall, the model has done a pretty good job in detecting infrastructure across the different settings. And so here's some visual results from the model predictions. So you can see Prudhoe Bay. The model has done a really good job detecting pipelines and roads and non-residential buildings on top of gravel pads, right? And then here's some results from the rural and medium density settings. So you can see the model is really successfully able to detect different kinds of detached houses and even unpaved roads in Point Hope, Alaska. Then you have the urban setting. So I'll just pull this up for a little bit. So if you look at Norilsk, Russia, you can see that the predictions are kind of sloppy here. So the model is able to detect the buildings and the roads, but it's overestimating their boundaries for some reason, right? And then also here's some results of runways and storage tanks. So now I'll talk about some of the challenges. So going back to the class imbalance issue that I mentioned, in the training data set, there's a really heavy imbalance towards background or non-infrastructure pixels. And this is a pretty common issue in deep learning, machine learning, but in this case, I think it's an unavoidable issue because infrastructure is on average, it's small and sparsely distributed across the Arctic. So naturally, you're going to gather a lot of background in the training data set, right? So this is why I've used a class-weighted cross-entropy loss function, which basically can be used to force the model to learn your minority classes. But it seems like it's actually weighting the minority classes too heavily, which is causing over-segmentation of these buildings, like you can see here. And then, going back to this, the Norilsk, Russia predictions. So when it comes to these complex urban scenes, defining their semantics is pretty difficult because it's really unclear what should be labeled and how it should be labeled, right? So, for example, in Norilsk, typically what you see is these apartment blocks configured together with impervious surface covering the base of the buildings. And I think that these might be parking lots, let's say, but I haven't labeled them because it just takes too much time. But it looks like the model is still detecting this as some kind of infrastructure. So, I'm struggling with this question now. Should I label these areas and what should they be labeled as, right? So you can see in the ground truth masks, I haven't labeled this, for example, kind of this impervious area, but I have labeled these buildings here. So finally, to talk about some of the next steps here. Firstly, determining the optimal model training configuration. So experimenting with different image pre-processing methods, data inputs. So maybe Arctic DEM might help with building detection, different model architectures, etc. Right? And also investigating model transferability between different built environments. So if I train a model strictly on rural settlements, how is the model going to perform on urban settlements? And then finally, and most importantly, I think the ultimate end goal of this research is mapping infrastructure across large areas, possibly in targeted areas where we know the model is going to perform well, and conducting a high resolution risk assessment. So I put together this figure that kind of synthesizes the recent literature on the Arctic infrastructure hazard risk modeling framework. And so this has been put together in recent years by a number of authors to answer this question of how permafrost degradation impacts infrastructure. And this is kind of all centered around calculating and mapping the potential for permafrost geohazards to occur in the future, right? And this depends on a number of major variables like future active layer thickness, future mean annual ground temperature that's simulated from different climate change scenarios, and other kinds of variables like ground ice content, sediment content, and slope. And so this potential is based on something called the hazard index, which basically represents this potential. So there's a number of different hazard indices that have been developed in the literature. But so, for example, you have something like the analytic hierarchy process space index, which is a ranked multi-factor approach that takes in all of these different variables and weights them based on their importance, sums them up. Then you have something like the settlement index, which measures the potential for ground subsidence. And this is basically the product of relative increase in active layer thickness and volumetric proportion of near surface ground ice. And so ultimately then these different zones of geohazard potential are co-located with infrastructure using the most available data to answer this risk assessment question, like how much and what kind of infrastructure falls within these different hazard areas, and what would be the cost to replace the infrastructure if it were damaged in the future, right? So this is where I see this approach coming into the big picture. If we can produce a Pan-Arctic map at a high resolution, this could really help improve this risk assessment studies and get a high resolution, accurate estimation. And also I see some potential for inserting the ice wedge polygon map produced by the Maple algorithm in here, because you can actually estimate near surface ground ice based on the area of these ice wedges, if you have a map. So let's see here. Yeah, so that's it. Thanks everybody for listening, and I guess I'll take questions now if anybody has them.
Yeah, I have a quick question. So I actually posted in the chat. So Norilsk is well known for having exceptional amounts of pollution, aerosol pollution, because of Norilsk nickel plant in the area. That is like lights up on our images of nitrogen emissions like a light bulb from space. And I am wondering, because Maxar doesn't clean the imagery before they give it to you, they doesn't clean the imagery for aerosols. I wonder if the high optical depth of the aerosols is throwing your model off.
Yeah, sorry, I missed your question. So actually I have noticed that closer to the nickel plant.
Yeah.
And I kind of, and that's kind of why I actually avoided that area, because it was so, there's so much smog, and I'm like, this is not going to work. So,
Yeah, the visible smog is one thing, but there's also the invisible one. You're using multispectral imagery, and it may be useful to wash the images first through basically doing an atmospheric correction. Using a product like Modis aerosol or something like that to to basically adjust for the absorption and scattering of aerosols. Clean up the images, because you're going to run into a similar issue with anywhere where you have you don't have to be over a forest fire. You can be well downwind from a forest fire, and where the smoke plume is not really very obvious, but it's there, and it may be there enough to throw your algorithm off.
Okay. Yeah, that's
and because you're with Maxar, you're operating on visible channels. That is exactly where the highest impacts of aerosol and ground level ozone as well are. Ozone absorbs very heavily in red, green, and blue. And so it's highest, the ozone absorption is highest in the blue channel, then medium and green, and still there. We still correct for aerosols when we use the 0.6. We still correct for ozone when we're using 0.65 micron channel, which is the red one, equivalent of the red equivalent in Maxar. So, I mean, the ozone absorption is a big one there. And at any kind of an urban site that you are looking at, and that's the thing, you may not be able to visually see the smog, but it's going to be there as a subvisible haze, which can be detected with other instruments. And it might, is regularly, because you're dealing with clear sky imagery, all those all the algorithms for other satellites that work for detecting aerosols and these trace gases also operate on clear sky imagery. So you kind of have a good match there. And it might make sense to you can even do such a simple experiment of taking a forecast model that produces the total column ozone, for example, and washing the data through doing a simple Beer's law correction, and washing the images through at least through the ozone, because that's a big factor when you're doing this kind of stuff.
Yeah, Gala, maybe it makes sense, maybe it could be worth to look into this. You could help us, since you're part of the development team, you could help us, identify a place where we have a lot of smog and to see how it does in the imagery for that. Hopefully,
yeah, I mean, I can certainly, because we already, this is washing the data is, well established. It's a well established methodology. We've been doing it for 20 years, and we have all the codes to do that. So
perfect. Yeah, so let's get back to that later, Gala. I think this is
it might be worth washing the imagery first and then feeding it through your algorithm.
Yeah.
Maybe,
thank you.
If I can have a question, so maybe that jumps kind of in that direction. So thanks. First of all, thanks for the question, for the great presentation, Elias. It was really good to see. Do you use any kind of augmentation, and which ones? Because these can, especially augmentation techniques, can especially then handle, dirty images and kind of also help with that. Do you use? Okay, there I see.
Yeah. So just the basic geometric augmentations. Yeah.
Do you also do some, I don't know, noise addition or brightness, whatever contrast stuff? I think that might also help, especially also maybe in kind of polluted environments when you add some noise or so. You can especially trained for that, or maybe that helps. Depends, I guess, a little bit on your resources and computational stuff. So that might be another thing. And what I saw, like little suggestion, which you also already suggested, with hyperparameter tuning, I saw this kind of little jump in accuracy when you change the learning rate, right? So if you go to the training curves, I guess that's where you change the learning rate, I guess, right in the middle after, I don't know, 25 epochs or so.
Yeah.
So playing around with the learning rate scheduling, etc., I think would be a good thing to see, because that kind of helped me quite a lot in my models to test that. And your data set is not too crazy,
Yeah.
not to test that and play around with that.
Yeah, definitely. This was, I'm going to do a whole lot more of that stuff. I just tried to get kind of the bare bones simulation first, but
yeah, sure. Definitely.
Yeah.
But really looks really good. It's super interesting. And we also had a student presentation on kind of similar topic, who we're also kind of trying to use some deep learning for mapping infrastructure in our course. So pretty good to see also some progress and that you're using quite good and advanced stuff.
Yeah, thank you.
Thank you. Yeah, don't be shy, speak up. Elias is at the phase where he's really hoping to get some feedback on the types of classes he organized, and also the choices of
Elias,
training places.
Shandy, if you guys have, and this is a simple one because this just needs visible only. If you have any Maxar data that like has like from Norilsk or from China or wherever, I can try running the chemical wash basically on this data and see how it changes, how things change.
Yeah, definitely.
Thank you.
We can look into it.
Because all I need is the visible. We don't even have to deal with the cross registration or anything like that for the SWR.
Awesome. And Sergio has a question in the chat. He says, great talk, thank you. Did you filter out images with clouds? And did that limit the total amount of candidate images?
Yeah, we looked for cloud-free summertime. So yeah, it definitely did. Yeah, so we try to avoid that kind of stuff. So thanks.
Elias, you want to mention? Yeah, maybe you want to mention the work that you guys are doing also with Gala on the cloud part. Do you want to maybe just briefly bring it up?
Yes, that could definitely all be integrated into one pipeline. I don't know. We haven't done too much with the cloud algorithm yet. We haven't tried it on any sort of deep learning approach yet, but yeah.
Yeah, so just to share with everyone that we recognize that because of the cloud presence and that the Maxar imagery is there's a big data set, but it's still limited. It's not taken every day like planet imagery or something like that. So we recognize that there's more information to get out of this imagery if we can have a good cloud mask. So between Elias, Shandi, and Polar Geospatial Center and Gala, they're exploring to see if we can map clouds out of the Maxar imagery. And thanks, Shandi. And then create a cloud mask for the Maxar data specifically that are at PGC. So that's in the works as well. Let's see here. So Elias, would you need some
listening to a talk,
help or assistance or from people across, like outside of Alaska? in
Sally
regards to?
sent it to me. Let me see.
Okay, we have someone with an unmuted
deep
mic
learning.
here.
Yeah, sorry, could you say that again, Anna?
Yeah, since you have such a wonderful crowd here, or audience here today from across the Arctic, is there something specific that that you would like feedback on, or any kind of knowledge that you feel that you could benefit from and create a stronger map, like people knowing their community very well and their buildings, and more training data somewhere, someone to look over your training data, or yeah, anything that you could see would be helpful to you.
That is the one thing, the one question that I could ask, you know, going back to, let's say, places like, because it's really the urban areas that are really difficult to figure out, like Norilsk, Russia. So I think we have maybe some Russians in the audience that maybe could provide some insight on this. I mean, if we want to map large cities like Norilsk, large urban centers in Russia, is it important to also know the extent of the impervious cover on its own, right? Because there's, I mean, these urban areas have a lot of impervious cover. Like, for example, like I said, I think these areas, I know it's hard to see because it's just a small tile, but you know, this is, I think it's probably parking lot or courtyard kind of thing that's happening. So the question is it important to know this flat impervious cover as much as it is to know the buildings themselves? You know, I mean, maybe anybody has insight on that. That's one question that I would ask. But you know, other than that,
yeah, any thoughts on that from people? Like if we do have larger communities like cities with asphalt and pavement, is the information of knowing where we have pavement, would that be useful? I could see it from a hydrology perspective, for sure, how runoff would and infiltration would work.
Oh, Sergio just brought up a really good point, because, oh, actually somebody, Dimitri asked a question before that, but real quick, yeah, Sergio, actually this is something that we're looking into right now, because I'm in the next training run that I'm going to do, might try to input Arctic DEM, because this actually might help the model you know, kind of differentiate this impervious cover from buildings too. So that's a very good point. Let's see, Dimitri, should I read out the question?
Maybe read out the question. Yeah, do that.
So very useful presentation, thank you. I propose to use the infrastructure clusters and linear objects intersections as the special risk factor. The impact zones are larger in similar conditions.
I mean, if you have 2 or 3 buildings, it's the one result. If you have a large cluster, maybe you can classify
Okay.
the amount of this cluster to taking into account when you calculate the risk, when you risk assessment.
Oh, okay, yes, it's definitely, yeah. Yeah, that's a good point. Thank you. Yeah. Yeah, okay. Anything else, Mike? Okay.
Would it be useful where, yeah, so you have one industrial zone that you're mapping, Prudhoe Bay, like would it be useful to have another one somewhere else, because to help strengthening that part and increase, I think, because you had about half the training data in industrial versus other classes, groups.
Yeah, that's something I do recognize that I should probably be targeting more industrial areas. It's also, I mean, because, you know, this is Prudhoe Bay oil field. It's a specific industrial site. There's also, I also acknowledge that you can find, let's say, pipelines, oil gas pipelines that are running across the landscape, and it's not one specific site, right? You can't just pinpoint it down. So there's also areas like that. Yeah, I have been looking for other industrial sites across the Arctic. Maybe if anybody in here knows of any, let's say, maybe really well-known sites that I could target besides Prudhoe Bay.
Depends, I guess, what you want to look at. More kind of oil and gas extraction, which is kind of a bit similar, I guess, because it's a bit more spread out, but there might be also mines. So big mines are, I guess, pretty different to oil and gas extraction. So there are a lot. I mean, if you stick to Alaska, there are some big mines. I don't know, Red Dog mine maybe is interesting, or in Siberia there are a lot of oil and gas fields like Bovanenkovo in Yamal Peninsula, or around Surgut. There are also a lot of like oil fields which are super interesting. It's also pretty interesting. So there are many places. Or I don't know, big diamond mines or so in Canada or Siberia. There's quite a lot, and I guess having it, but kind of these two types, as they are pretty different, to get some data from them or from these places would be good, I guess.
Yeah, that's a good point. But one thing I did want to avoid, because I heard, there's a number of people that were bringing up, let's say, including mines as an infrastructure class, for example, like you were just talking about, Ingmar. But the question is, if these kinds of things are actually built structures rather than just like a modification of the landscape, that's one thing that
I would say there are actually some built structures, right? So there are, I mean, housing structures, there are, I don't know, storage, whatever. I think then there's quite a lot actually. Maybe they are not as permanent, but they're there, and especially in the oil fields, they're I guess rather permanent for, I don't know, maybe a few decades or so.
Okay.
And
Yeah.
for kind of traditional or industrial, I guess, Norilsk.
Yeah.
I find a lot of stuff there.
Yeah, there was a lot of it's a gold mine of industrial infrastructure, no pun intended there. But I did avoid it just because it was, again, very, very complex, because that's also the challenge, is knowing what to actually label and how to label it, because some of these sites are so messy. There's so much pipelines and all sorts of things overlapping each other, and it becomes very, very messy. But yeah, I was gonna say one other thing, but now forgot what I was gonna say. But anyway, yeah.
Sergio has a question in the chat again. Are you pen sharpening the images to increase resolutions?
Is Chani still here?
He left. I'm pretty sure there is some pen sharpening done by PGC before they send it to you.
Yeah, so they are pen sharpened.
Yeah, and I think Shandi also didn't have a paper out on it a couple of years ago as well, of different approaches to pen sharpening and how it affects the later results in the deep learning modeling. So
yeah. Okay.
Yeah.
I mean,
yes.
Oh.
See if we had one hand up. Yeah, Juliet, go for it.
Yeah, thanks for the presentation. That was really interesting. I was wondering if you could speak more to how you're using the weighting for the classes. So you talked about like the impervious, like pavement and such, like the impervious background that isn't as important as the structures themselves. I think you called it class weighted cross entropy loss. How does that work?
Yeah, so yeah, basically this loss function basically controls any the loss function in general controls how the model learns and basically how it updates the model parameters over the training process. And I'll try to explain it as best as I can because I'm not really too keen on the heavy technical details. But I mean, basically, you know, you figure out what's the frequency of a given class in your training data set, right? And if the class is very large, you know, you could give it a very small weight, right? So it's the inverse frequency. And basically, let's say the model does a good job in detecting a really large class. The loss function makes sure that the model's not rewarded too heavily for doing that. Rather, if it's doing a poor job detecting really small classes, the model's going to the loss function is going to penalize the model very heavily for not learning the minority class. So basically, it's just a way of it really controls how the model learns. And so a better way to illustrate it is just to bring up the point that before I brought in a class weighted loss function, the model wasn't able to detect like these. If you're like looking at this tile here, the model wasn't able to detect these really small houses at all. It just wasn't able to do it because there's so much background, like there's so much landscape background that I haven't labeled. But once I brought this class weighting in, you know, all of a sudden, you know, it was like magic. All these buildings started to pop up in the model output. So yeah, I mean, hopefully I was able to answer your question there, or at least give some insight. But,
Yeah, thank you. That's interesting.
yeah.
Yeah. So, okay, here's another comment in the chat here too. I think from Sergio, you might consider testing another deep learning architecture to see how it compares to UNet++.
Yes, Sergio. That's going to be one of the next steps. Actually, I used, when I was first doing this work, I used UNet on its own, the original UNet, and actually it performed, the performance was a lot, the accuracy wasn't as good as UNet++. But yeah, you know, there's other things like Deep Lab and you know, things like that that would be interesting to see how the different modules affect the performance. So I know Ingmar knows a lot about that stuff too. So yeah. So okay. Yeah. Thank you, Sergio.
Right. And I wanted to share too, you know, so Elias is working on this to map it across the Arctic, and through the work that Shandi and Elias have done with Maple, there's already a workflow in place to use Maxar imagery and deep learning across the Arctic region. So it's very likely it will be successful to be mapped across the Arctic, but of course, it's great to have the input from the community who will potentially use the data to make sure that we get a good working model. So I think like with the IceWedge polygon data set, we have uploaded the high ice region according to Jerry Brown's map. The high ice region results, the first results are uploaded on the Permafrost Discovery Gateway, and they actually have a new version created that we're trying to get up here in the next couple of weeks as well. That is a little cleaner because we recognize the value of getting the data up there and hear your feedback on where it's working and where it needs more work, because it's such a big data set that not just one single person can go through it all. So we're hoping to have also some tools in the Permafrost Discovery Gateway where people can submit reports over their issues with the data set, so that those report submissions can then hopefully be integrated into the training data set and help refine future versions of the data sets, because I think it's we see it as a collaboration within the community to get these big data sets in a good enough shape that people feel comfortable working with them across panarctic scales, and that requires teamwork from people knowing their backyards to people knowing how to run and create efficient workflows. So good. Yeah, Elias put his email in the chat as well if you want to connect with him directly. See if there's any more questions or hands up.
Yeah, I think that's it.
Yeah.
So I can stop sharing now. I think we're done now.
So thank you everyone for joining us, and yeah, we welcome you to the next PDG webinar, which will be in February 23rd, and that's when Shandi Vitharana, also from UConn, will present on the ice wedge polygon map, and hear your feedback on that. So as we're trying to get the first version of it, working on getting a first version published, and so we recognize the importance of hearing from you all on what you like to see done before we call it good for the first version of it. So February 23rd, same time, same link. Hope to see you then, and thank you for joining us today. Thank you, Elias.
Okay, thanks everyone.
Bye.
Bye.
Thank you. Bye.
Thank you so much. Thanks for joining us.